Okay. Is it paused again now?
Okay, because I'm using the laser pointer on the screen because that'll be captured on the video.
Yeah,
I figured that's better.
better for the video.
Yeah. So anyway, I'm on the keyboard anyway,
Okay, I think we're good to go this morning. Our speaker needs no introduction. And take it away.
All right. Good morning, everyone. Great to see you again. So we're going to continue from yesterday, talking about the other two techniques in the diffuse optical realm, time domain, and what we usually technically called time frequency domain, although often informally called frequency domain. And a review of yesterday, we talked about tissue optical properties and chromophores, the Beer-Lambert law, modified Beer-Lambert law, and Beer's law. And we discussed spatially resolved measurements and spatial frequency domain imaging. And along with those, I gave you some examples, talked about inverse models and trade-offs with those inverse models. And we didn't have time to talk about wavelength selection, but I'm happy to talk to you about that if it's something you're interested in. And in continuous wave, we had spatially resolved measurements. We had this kind of measurement geometry, and we had a region that was scatter dominated, where you're close to the source, where you have short path lengths of photons. Photons haven't traveled long enough to undergo much absorption, so absorption doesn't really change your measurement. And then the tail here is scatter and absorption dominated. Then we talked about spatial frequency domain imaging, how that's a Fourier transform away from spatially resolved, and how we can also segment out photons of different path lengths by using spatial frequency. Higher spatial frequencies are similar to short source detector separations in that they make you more sensitive to shorter path length photons, and thus more sensitive to scattering in, for example, the near infrared. So today I'm going to start with what I'll call some bookkeeping and some resources. I want to dive into a little bit more about chromophores and extinction, and then talk about phantoms and system calibration before moving on to the time domain and time frequency domain. Then we'll do a comparison of the techniques and talk about some example applications. Just like yesterday, I think it was fantastic how it turned into a discussion, and there was lots of questions, so please do the same today if you're so motivated. Remember, our learning objectives are to gain both an intuitive and quantitative, but also practical view of the diffuse optical technologies and how they work. So in that vein, let's talk about chromophores and extinction values. So I showed you this figure yesterday. Remember, this is from a hypothetical tissue, a healthy breast tissue. We have the red and blue lines for oxy and deoxyhemoglobin, and then water in black and lipid in the green color. And these absorption spectra have shapes to them. And what is causing those peaks and valleys? You can actually be in this field for a long time and kind of have no idea why these spectra look like this. So let's talk about it just for a minute or two. Okay, so at shorter wavelengths, these peaks you see down here in the 600 nanometer range for hemoglobin, these are caused by what's called electronic transitions. When you have energy at fairly high energy levels, meaning short wavelengths, you can get an electron to be excited from one electronic state to another. Now, what does that mean? This is an energy diagram where you have energy on the y-axis and intranuclear separation on the x-axis, and this is related to the heme porphyrin molecule. We can get just the right energy to get an electron up into this higher energy state. These little vibrations are vibrational states. They're much lower energies. So at specific wavelengths, you can have this electronic state change, excite the electron to a higher orbital, and causes change in the internuclear separation afterwards. And then that would normally cause a very sharp peak in the absorption spectra, but they're broadened due to these vibrational sublevels. Now this one is a little bit harder to understand. You have to dive into a little bit deeper, but if you don't take away anything else, at short wavelengths, invisible and 600, these are electronic transitions. And as you go to longer wavelengths, you have more vibrational causation related to these peaks. So all these peaks you see out here for water and lipid, they're due to H2O or CH bonds stretching or bending in different ways. And in fact, to be a little bit more precise about that, the fundamental frequency of those bendings or stretching happens even further out at lower energies in the infrared. And what we're seeing are harmonics or overtones of those stretches and bends. And so we see them way down here at 970 and 1180. So that's the vibrational overtone for the OH bend. And 1450, the first overtone of OH stretching. Okay, so short wavelengths, electronic transitions, longer wavelengths, vibrational changes. And then people have measured these absorption spectra in spectrophotometers, and you guys had a lecture on inverse adding doubling. That's one way to do it. And I showed you this figure yesterday where we can use Beer's laws. If we can measure mu A, we want the concentration to use as a biomarker, we need extinction values. And so that this is not mysterious to you where these extinction values are from, they're in literature, but I want to show you a few sources, few specific sources. Do you guys know about the OMLC website, Oregon Medical Laser Center? Some yes, some no, okay. So this is a website that's been around for a long time. You can see who the copyright is from, and Scott gave you guys a lecture, right? Did he talk about his website? Anyway, a lot of us use it. You can see there's links for different chromophores and their associated spectra. You can click on them, and then you get extinction spectra from different literature sources. It's very convenient, and there's comparisons and back and forth. Comparisons between different literature sources. So this is often a first stop. Each lab kind of maybe has their own favorite extinction sources. This is what my lab has been using, and it's all annotated like this because we're working on a review paper about SWIR optical properties in tissue, but we've combined the resources that go from visible all the way out to SWIR. So for example, the first 3 lines are about oxy and deoxyhemoglobin. And you can see this first one from 430 to 599, we use Scott Prohl's website. And then in the middle here in the near infrared, we use this Zylstra, which is a very famous source. It's actually published in a physical book. I know there's at least one copy of the physical book in this building because I've seen it. It's often out of print, so it's like $400 on Amazon if you can find it. But it's also tabulated online. And it's tabulated in Irving Biggio and Sergio Fantini's textbook. They're quite useful textbook if you've seen that in biomedical optics. And I won't go through all these, but you see each of them has a citation. And on the next page, I've just given you the relevant citations for them. So these are the papers if you want to look them up. And they're, they don't start at 1 because this is pulled from the review paper we're working on. And then I want to give a note of caution. I mentioned this briefly yesterday, but the Beer-Lambert law can be written in 2 different ways. Right? Beer-Lambert law shows us the relationship between light in and light out, but it can be written in log base E or log base 10. And the extinction values are different depending on which base you're in. And so you need to know which base the extinction values are given to you in. And then if you want to use Beer's law, mu A equals extinction times concentration, you want to be in log base E. The mu A is always given in log base E. So for example, the hemoglobin extinction on the OMLC website is in log base 10, which is why we use that 2.303 to convert down here to get it into log base E. This all sounds like silly little stuff. It'll really frustrate you if you don't have it right. And I wish somebody had kind of told it to me like this many years ago. So take it for what it's worth. Okay, phantoms and system calibration. Okay, yesterday we were talking about you take a measurement that looks like this, and then you get a result that looks like this with your instrument, where the y-axis was diffuse reflectance. But we didn't really talk about what's between these 2 steps, right? The data that comes out of your instrument is not going to look like this because it's convolved with your instrument response. And so that means, say you have this set up with a broadband light source and a spectrometer. The light source doesn't have equal light output at every wavelength. It can look quite different depending on its color temperature. Likewise, your detector will have different quantum yields at different wavelengths. And you have to take all that into account. And how do you do it? Otherwise, you're measuring some combination of what your system sensitivity is and your actual sample. So that's one of the reasons we use phantoms. And what you're seeing here is a picture of our quote unquote phantom library from my lab. It's just phantoms that have been made over many years. You can see we have many that look like blocks, some that look like fingers, some that are more soft, some that are more hard. This one is made to match the mechanical properties of breast tissue. And then we take our probes and put them on top of the phantom. And we use these for calibration and also for what I call preclinical testing, preclinical in this case, meaning just before we go into the clinic, not on small animals. We make multi-layer phantoms. You see some of these phantoms have holes in them for channels where we send fluid in that can have different optical properties. And so everybody has different phantom recipes, and there's many papers and some very good review papers on phantoms. We tend to make silicone phantoms, silicone being the base material, and then add titanium dioxide, which is an easy to obtain ingredient, and like in the paint on the wall, typically has titanium dioxide that provides scattering. So that's some of the back reflection you see. It's a nanoparticle that has a size distribution of scattering centers that match pretty well to tissue. And then we use a dye. Nigrosin, India ink are popular, but there's many, many others. Since we've been thinking about the SWIR, nigrosin and India ink, their absorption falls off with wavelength. That means it doesn't match well to the absorption out here at longer wavelengths where water and lipid are very strongly absorbing. So we have to take that into account. It's often difficult to make a phantom that matches tissue optical properties at a lot of different wavelengths, especially over large bands. So if you want to simulate a lot of different tissues at different wavelengths, you might have to make different phantoms. But how do we use these phantoms? So one way we do this is, for example, for these diffuse optical techniques, let's say we have this material and we know the optical properties of the material, mu A, mu S prime, and sometimes G. We can use a forward model, which we talked about yesterday, to go from optical properties to some known diffuse reflectance. It just means a material with this optical properties, this geometry, we know should give us a diffuse reflectance that's X. We take an experimental measurement with our device and we get some measured value M. It's not going to be the same as this value because M is a function of our instrument response function and the diffuse reflectance. But we can apply a calibration factor if we assume that the instrument doesn't change over time or between the calibration measurement and the measurement we take, for example, on tissue. And we can also assume, or we can validate that the instrument is linear in its response. When we take a new measurement, M of tissue, we can multiply it by this factor, RD over M from the phantom, to get RD of the tissue. Does that make sense? You're just canceling out the instrument response. Again, assumes linearity, so we typically measure the linearity of our system. So we know under what conditions this is true. Yes?
So Darren, you're mentioning, at least in the title slide, this is for CW, right? So for CW, we typically do, say, spatial, for argument's sake, let's just say we're doing a spatially resolved measurement. So in that case, would the IRF depend on source detector separation?
We would typically have a calibration factor for each source detector separation. Yes, the coupling can be different. If there's any difference in the fibers, just would want to do it for, yes, for each source detector separation, absolutely.
So I just want to emphasize that's not a constant, right? It is a function of your measurement variable.
Yes, exactly, yes. Yep. You can do this for frequency domain or the techniques we'll talk about today as well, not just CW, but yes. Yes.
So how often is your instrument response linear? And what happens if it's nonlinear?
Oh, yeah. Well, how often is it linear? So it all depends on what device you're building, what the detectors are, what the light sources are. So that's why you have to test it. I don't know. It's unique to each device. So, and often any instrument will be linear over a certain range. And then outside that range, you'll see nonlinearities. And you can potentially correct for those nonlinearities. Like most CCD detectors or photodiodes become nonlinear as you get close to zero counts. And then also as you get close to saturation, there's a roll-off. So you either use that detector in the linear range or do some kind of nonlinear correction to squeak out that extra performance. And then another related question is, how long does your calibration factor last? This is an interesting one and one that people have studied. You know, if you have calculate your calibration factor today, can you use it tomorrow? What we use in practice in academia, in my lab, is before we take a measurement on a patient, we do another calibration measurement. And often after we take a measurement on a patient, we'll do the calibration measurement again and just see if those calibration factors change. Now, I was just at Modulum yesterday. They have determined that the device is pretty stable over time. So you don't need to take a calibration measurement as often. Maybe you do it once a month or once a year. I'm not saying that's what they do for their device, but it's less often like that. So it just kind of depends, and you have to test to make sure that it's stable. So how sensitive is your detector to thermal changes, and are you controlling the temperature inside the box? Thermal variations can affect your response quite a bit. We've dealt with that a lot, especially for the time frequency domain measurement I'll show you later, where we're running an avalanche photodiode at high voltages. It's a long-winded answer. Hopefully
Thank you.
Yeah.
Any other questions? This is a super important topic and one that is kind of not often overlooked or not really exposed in detail in kind of a formal lecture setting, but this is where the rubber hits the road.
Yeah,
In
exactly.
the lab. Any other questions?
Even the phantom recipe, this is sort of something that's like passed, not through papers typically, but like through protocols from lab to lab. And I'm not nobody's trying to hide it. It's just can be hard to publish. Just a phantom recipe, depending. So if you want a phantom recipe, you got to ask. Yeah, exactly.
So is there any change in the influence of the IRF if you are doing absolute measurements or relative measurements?
Well, let me go to this slide. I think this is what you're referring to. But for the case of the modified Beer law or the differential modified Beer-Lambert law, where you're looking at changes in intensity, again, as long as your system's linear and these changes aren't too large, you don't necessarily need to do a calibration, right? Those relative changes, you're kind of off the hook. It still could be good to measure a phantom periodically and make sure your instrument's not changing. But is this what you were in fact referring to? Yeah.
I guess along those lines, the reason why I would consider doing a calibration even with relative is you might have an offset, right? So then that's changes all the relative changes as well.
Yeah.
Do you assume homogeneity of like titanium dioxide when it and when the silicone cures? I'm assuming some of it falls down.
Yeah. So what people have done is they'll take these phantoms and cut them in half. And then, so you can see the cross section and then try to look to see if optical properties change through the thickness of the phantom. And I think mostly we're confident that they're homogeneous, but not fully confident, right? It's there's enough there that's a little bit hard to publish on that sometimes we'd love industry to kind of solve this problem for us. And there are some new companies, Biopixis and who's Ethan's company? Quell, yes. And they make phantoms that you can buy. They'll give you the optical properties of them. Typically, they use time domain measurements we'll talk about in a moment. Although even then, you got to be careful. Are you sure about the optical properties or not?
Collaborate with the International Space Station and make a phantom at 0G to make sure we get no settling.
Exactly, yeah, yeah. You also might ask, well, how do I get these optical properties of this phantom? So you can take a piece and do something like inverse add-in doubling, potentially. That's probably the closest to the first principles. You can use another phantom with known optical properties and use an instrument to measure a new phantom. That's probably what's used in practice a lot. That's what we've used in practice. And actually, a lot of the phantoms in our lab go back to a phantom that was developed in Bruce's lab called Akron 09. You know, we still think about a lot, like, are the optical properties of that phantom correct? Because it would be downstream, it could affect a lot of what we do. Well, there's some phantom anxiety.
Darren, I somewhat recall there is some effort at NIST. Maybe, are you aware of the effort at NIST? And
I've heard whispers, and I think they have some RFAs related to teams that have put together phantoms that, you know, people can trust, but I don't know much more than that. It's a very important part of the field, a little bit less sexy part, but. Yeah. All right, time domain. So time domain diffuse optics, the third method we'll talk about. Here, we send a pulse of light into tissue. That pulse tends to be on the scale of picoseconds. That pulse of light travels through tissue and it smears out in time. This is the detected pulse at some source detector separation. We call that the temporal point spread function. The shape of this temporal point spread function encodes information about the tissue optical properties. And it does this in a way that's kind of nicely intuitive. Here's what a time domain instrument might look like. Here's our sample. We have a light source. It has to be pulsed. This already kind of kicks up the cost of these instruments because a pulsed light source tends to be more expensive than a CW light source. Then we detect. We have to have a detector that can detect single photons. And we have a time-correlated single photon counting module. This is the electronics that count when photons arrive at that detector and record them in a histogram. And typically, I'll just go back one slide. What you're doing is it's hard to get enough photons to build this temporal point spread function under one pulse. So the pulse gets repeated and you're building up a histogram of arrival times to build up this temporal point spread function. But the repetition rate is very small, 0.1 microseconds, for example. So you can do many, many pulses over a fairly short period of time. But you can see this requires very precise and accurate counting on nanosecond time scale. So these systems and these electronics are available, but they cost money, like tens of thousands of dollars for the electronics and detector. And if you look, this is a nice simulation from Chin Feng's group at Northeastern, who does some Monte Carlo modeling. See a pulse headed into the skull up here, and you can watch it over time in the nanosecond time scale, how that light diffuses through the skull and the brain. And just give you a sense of space and time here. And so let's look at similar plots that we looked at before. Here we're looking at, you can still think of this as diffuse reflectance or detected optical power versus time in the nanosecond time scale. And we have our 4 different tissues. Here you can see the tails are quite sensitive to absorption, right? So these two are low absorption with high and low scattering, and high absorption with low and high scattering. Tail really sensitive to absorption. The beginning of this temporal point spread function is sensitive to scattering, right, at really short time scales. If you have higher scattering, you're pushing this back, the upslope is slower. Now, you guys should be able to tell me intuitively why this is happening, and it's sort of the same explanation for the other 2 techniques, but in a slightly different manner.
Darren, for clarity, what is your source detector separation for these?
This is an example from the textbook. I don't know what the source detector separation is, sorry. What do you guys think? Why is scattering affecting this? The beginning of the temporal point spread function and absorption more at the long tail.
Just as a hint, I think that the source detector separation is fairly long.
Large.
It's not close.
Yeah. Yeah.
Probably because the photons haven't had enough time to absorb, and the mean path length is still pretty short. So everything is just, so the beginning part is probably just scattering dependent, and then
Yeah.
at the end it's absorption.
Yeah, pretty straightforward answer, right? So you could think of time and path length as being closely coupled. So at these very close arrival times, you have photons that took the most direct route from source to detector, shorter path lengths, more affected by scattering. These ones that took their time to get to the detector, longer path lengths, they're traveling longer in the tissue, more will have the opportunity to be affected by absorption. And Vasan's right, as you change the source detector separation, these things can collapse on each other. Here, it's an example that's sort of showing the maximal differences. So we call the upslope here scatter dominated, and the tail is more absorption dominated. These things aren't exclusive, but if you think about the primary drivers, then those would be them. You can also think in terms of depth here. So your short arrival times are photons, as I mentioned, that took a direct path or more direct path from source to the detector, and your so-called the late photons have likely traveled deeper in the tissue. So this is one way people try to measure deeper tissue with the same source detector separation. They'll only, quote unquote, listen to the late arriving photons, and they know they've gone deeper in the tissue, which can be useful under certain circumstances.
Can you measure how big the tissue, like the tissue layers with just the reflectance information with this
Can you measure the
thickness?
of the tissues?
Yeah.
Well, you could develop a multi-layer model where thickness is one of the free parameters. If you had enough information, you might be able to extract optical properties and layer thicknesses, maybe for the top layer, but it's a lot to fit to.
Mm-hmm.
If you had some a priori information, like sometimes you could use ultrasound to get a layer thickness or get layer thicknesses from media, then you could say your late arriving photons are more likely to have traveled to the deeper layer.
Okay.
Yeah.
I guess in the sense of when you say deeper, how do you know where the cutoff point is for like deeper versus shallow?
Yeah. So in order to do that, or at least the way I would answer those questions is by doing modeling, right? Because it's going to be very dependent on the tissue optical properties and your source detector separation, right? So there's no hard and fast rules. There may be some empirical rules of thumb. I don't know, Boston, what would you do? Run some simulations probably, right?
Yeah. I just want to emphasize that time is directly proportional to optical path length, right? Because the velocity of the photons in the medium is constant. So, of course, just because you have a long optical path length doesn't necessarily mean that the photon necessarily went deeper. I mean, there could be
Right.
some photons, but I think the takeaway here is really the advantage of time domain relative to CW, because all you're measuring in a CW measurement is basically the integral, the time integral of this entire curve. And you're mixing, in some sense, photons that both took like the more direct path, as well as the ones that went deeper. And so when you have time resolved, you do have the opportunity with good modeling, good inverse solvers to get some depth sectioning, or to resolve layered geometries with a little bit better precision. And that's really important, like in brain oximetry, I mean, the standard of care right now, to the degree optics are used, are CW instruments, and they have a lot of problems with separating hemodynamics in the scalp from the cortex.
Right.
Yeah.
And why are picosecond lasers used? Is it to, I guess, make the whole system fast?
Why is the width of the pulse
Yeah,
and the
pulse
picosecond?
duration. Yeah.
If you want to capture these nanosecond timescale changes, right, and the timing of this temporal point spread function is going to be dependent on the arrival times of the photon, which is going to be dependent on tissue optical properties, right? If you want to resolve what's happening here in the nanosecond timescale, you need a pulse that is finer, narrower than nanoseconds. So you could do picoseconds. You could have a narrower pulse than picosecond. That's fine. In fact, you get arguably better information, whether it's usable or not. But it's just the narrower the pulse of a laser, the more and more expensive the laser gets.
Right. If you go down to like the femto range, do you get nonlinear effects, and does that mess up your measurements at all?
If you do, I don't know. I don't know about it. I don't know if anyone else does.
Another way to answer that question, Brian, is to really consider the intrinsic timescales of the photon in its travel through the tissue. based on either absorption length scales and scattering length scales. And so you have a length scale for single scattering that's given by 1/μs, and you have a fixed velocity in tissue. And you can actually calculate on average what is the mean time. We've talked about mean distances between scattering processes. There tend to be between 10 and 100 microns. That is directly linked to a time scale for scattering and similarly for absorption. And so if you go through those calculations we actually did in the very first lecture, I'm going to revisit that in the lecture. And that will give you some insight as to why you need picosecond pulses and why this dispersion is on the nanosecond time scale. So we're going to talk about that.
I guess I'd say why you need at least picosecond pulses, right? I'm not dictating smaller. The nonlinear effects I'm not as sure about, but yeah. Okay. So I'm going to leave time domain there, except to say, let's see. There's a few people in the US doing time domain techniques. It's actually more popular in Europe for whatever reason. There's folks in Spain and in Italy doing a lot of time domain measurements. They're really the world's experts in them. I'll show you one or two examples of that later. And then time.
The early pioneer was from University College London, right? David Delby was kind of the first real pioneer. Of course, the Italian group has done a lot of innovations.
That's right. And if you guys have taken like a signals and systems course, you kind of know if you have a LTI system and you want to know everything about the system that you can, you want to send an impulse, you want to get the system's impulse response function, right? So I think of time domain as the kind of the top of the diffuse optics hierarchy, gives you potentially the most information and other things fall out from it. For example, time frequency domain is related to time domain. Here we're modulating light source, typically sinusoidally. It doesn't necessarily have to be sinusoidally, but you get a pure tone that way. And you measure how the amplitude and phase of the so-called photon density wave that travels through tissue is altered by the tissue. And this encodes information about the tissue optical properties. But just like our spatially resolved measurements, we're a Fourier transform away from spatial frequency domain measurements, but that Fourier transform occurs over space. If we do a temporal Fourier transform, we can go from time domain to time frequency domain and back. And if you remember from your coursework, if you have a cosine or a sinusoid and you take the Fourier transform, you get a single peak if this is 0 hertz that indicates that frequency. Likewise, if you have a delta function, an impulse function, sort of like the picosecond pulse we have in time domain, you have frequency content that's spread out evenly over all frequencies if that pulse is infinitely narrow. Now, as that pulse broadens, the frequencies roll off. But in time frequency domain, we're basically picking off some of these frequencies that are captured in time domain and using those to calculate optical properties. So the time frequency domain captures some portion of the information that's available in the time domain. And if we look at our same set of curves, but this time we have 2 of them. One is for modulation. So this is how much the sinusoidal signal decreases at our detector position. And the other is for phase. We see some relationships here, but they're a little bit complicated. We see that modulation rolls off with frequency. And here we're in the range of tens to hundreds of megahertz. And related to your question about the picosecond pulses and then the nanosecond temporal point spread function, as we transform, we want to capture the same dynamics, and the tens and hundreds of megahertz are capturing dynamics on the nanosecond timescale that are related to the time travel of photons for tissue optical properties. These are kind of our sweet spots, these modulation frequencies that allow us to differentiate mu A from mu S prime. And so in this curve, you know, I don't see clear patterns in this example between absorption and scattering like you do in the time domain. You see a little bit more in phase. These are the 2 low scattering and the high scattering. So high scattering accumulates more phase over a given source detector separation on average. But we have a lot of information here from the amplitude and phase, and we can fit that to our inverse model. And this does a really nice job of giving us absolute mu A and mu S prime. We can solve the diffusion equation in the time domain or the time frequency domain. This is one solution for the infinite media. And I'm showing you just so you can see, okay, we have a DC and an AC component to the modulated fluence. And this is expressed in this complex exponential where we have a wave that gets damped over time and accumulates phase. And so you can look up solutions. In fact, this is maybe the correct reference for the solution to the time frequency domain diffusion equation with different boundary conditions by Haskell and Schomburg way back in 1994. And just like with the other techniques, you can use the diffusion equation or solutions to the diffusion equation, or you can use Monte Carlo. So here's our measurement, reduction in amplitude and shift in phase. Let's look at some surfaces from a forward model. So here we just use one of our forward models in the frequency domain for different mu A and different mu S primes for a tissue. You're looking at the logarithm of the amplitude. So amplitude we're using interchangeably with what I showed you on the other figure as modulation. So the amplitude of the modulation of the detected signal. Yeah.
For clarity, this is for a fixed modulation frequency
This is for
And
one modulation
and
frequency.
one source detector separation.
And one source detector separation. Yes, thank you. And so what you can see here for a given modulation frequency, if you only measured the modulation for a given set of optical properties, we would probably get the same amplitude value. But when you add the phase information, now you can fit to this information simultaneously. The amplitude and phase gives you a more unique answer. There's one amplitude and phase that maps to one mu A and mu S prime under the conditions of homogeneity. And there are regions of optical property spaces where this is less true, where you might be not fully unique. So you have to be careful about that. And this comes down to source detector separation choice and modulation frequency choice. Yeah. No, not at all.
Squeaky wheel. I was looking at the y-axis of amplitude. It's many, many, many decades there.
Yeah.
Like I think 10 orders if I squint, right? So does that give you some insight in terms of ranges of optical properties in some sense that this technique is well suited for versus not well suited?
Right, because it's very hard to make any device that can measure over that many decades of any variable, right? But yes, you know, there's all these factors. One reason I'm hesitating is so you can use your model, figure out where you can find unique optical properties at what modulation frequency. But then you also have to think about the instrument. Instrument, you have a detector. It has to have a response that allows you to measure those modulation frequencies. And every detector has some capacitance. Capacitance, together with some of the intrinsic resistance, acts like a low-pass filter. And you have higher capacitance, the larger the active area of the detector. You want a large active area detector to measure a lot of these photons, especially at large source detector separations. But there's roll-off. It's very hard to measure at a gigahertz at 30 millimeters source detector separation. We typically use a 3 millimeter active area detector. If you look at the spec sheet from Hamamatsu, it'll tell you can only take measurements up to maybe 50 megahertz, but we use it up to a few hundred megahertz. We're just in the roll-off region where you really lose a lot of sensitivity and we're squeaking out extra performance. So all these things come together. Can you measure the actual amplitude change in phase-induced shift in a system? Likewise for phase, if your source and detector separation are close, there hasn't been much time, so to speak, or distance for phase to accumulate. And it's very hard to measure small phase shifts, right? Just any phase detector, this typically comes down to the electronics, has some jitter, has some precision, some resolution. So if you're too close, then you have a hard time measuring accurate phase shifts. And so you can shift to a higher modulation frequency where you'll accumulate more phase shift or give for a given source detector separation. And you run into the other problems of losing your ability to detect high modulation frequencies because of the characteristics of the detector.
Precisely. So I think what I'm trying to, great answer. You know, in some ways, you got to measure your signal over a certain range of temporal frequencies. And that range of temporal frequencies is linked to the actual optical properties. And as you get higher in absorption, for instance, the residence time of the photons in the sample, the mean time before they get absorbed, goes down, which then necessitates a measurement at higher temporal frequencies. And that's when you run into instrument problems. And you
Right.
kind of set that in a different way. So there is some dictating of domains in the optical property space that you're better positioned to be able to separate absorption from scattering, because at low absorption, you can actually get away with measurements of lower modulation frequencies.
Yep. You're kind of searching for the sweet spot for the tissue you're looking at, the instrument you have available to you. Yeah. Okay. And here's our inverse model. Same figure I showed you yesterday, but just so you know, you can use version of the diffusion approximation here. Your output of the diffusion approximation will be the modulation and the phase rather than diffuse reflectance. So depending on how you build your instrument, you can measure at a single modulation frequency, or it's common for a long time to do sweeps, where we'll measure frequencies over a broad frequency range. And you typically we modulate laser diodes. Laser diodes you can just buy off of Thorlabs. They modulate pretty well. So for example, for a typical measurement that we might take in breast tissue, here's a bank of laser diodes that we modulate independently, so one at a time often, through a frequency sweep, and build up amplitude and phase plots of how the tissue is changing those photon density waves. And then we'll fit for each wavelength an inverse model and get a mu A, an absorption value at those wavelengths. And then we proceed as before. We can use extinction coefficients and Beer's law to allow us to get chromophore concentrations. Now here, this is just for display purposes. We didn't actually calculate a mu A out here near where the water and lipid peak are. So it would be actually quite challenging to get water and lipid from these measurements and these red dots. You'd want a few measurements out here at 930 or 970 to help you do that. In fact, one of the difficulties with this technique is as you take laser diodes and you go to longer wavelengths, the capacitance changes and it's harder to modulate them. So we have difficulty modulating laser diodes at 970, for example, a lot of difficulty modulating laser diodes past 1,000 nanometers.
How long does a typical frequency domain measurement take? I assume it affects your frequency resolution once you do that Fourier transform, but yeah, how long do you usually modulate the light for?
Yeah, it's a good question, Anna. I'll show you a few example instruments, but it kind of depends on how you do it. Okay, so here you could take all these measurements sequentially, one at a time, and you're doing a frequency sweep. The integration time, so to speak, the measurement time for the avalanche photodiode can typically be pretty short, like maybe microseconds. And so this whole frequency sweep could just take, less than a second. And then you can play games where you're modulating each laser diode at a separate frequency, turning them on simultaneously, and then sweeping them in concert, and then disentangling all that information on the back end digitally, right? Because you can do Fourier transforms and calculate the amplitude and phase at any given frequency that matches with your wavelength. And this is a way to really speed up the measurement.
Okay, so what you're modulating is the input frequency for a given, but what's controlling the length of that single frequency measurement is the integration time of the photodiode.
Yes. I mean, unlike a CCD, the photodiode, you don't have the exact equivalent of an integration time. You just have conversion from photons to electrons and current that you immediately measure, right? So really what you need practically is to measure for long enough that you can get several periods of the cycle that you would need to do, say, a Fourier transform to calculate the amplitude and phase. So the measurement length, and this would be a analog to digital converter, your measurement length or number of samples for an analog to digital converter has to be enough in order to meet the Nyquist criteria in order to get at the amplitude and phase measurement.
Yeah, that makes sense.
Great questions. Any other questions?
So this technology has changed over time. This is a figure from Bruce. He did a lot of these measurements. This is from the Beckman Laser Institute back in the 90s. The instruments evolved to something that's on a big benchtop, optical benchtop, to this thing, which is refrigerator size. To 2014, when I was here, we had this thing called the MDOSI. And now every few years, I see somebody publish on a chip, like an ASIC, that has all the electronics built into it. And then there's two commercial entities, ISS, where you can buy a frequency domain device. It's actually spatially resolved, but also frequency domain. And then Nearwave, which is a startup company started by Tom O'Sullivan, who was also a postdoc here for Bruce. And they have this nice little handheld device that you can scan across the tissue. That's all frequency domain. So it's really come a long way. Back here, we would use something called a network analyzer to measure the amplitude and phase. Network analyzer is like a frequency domain version of an oscilloscope. It's for basically RF electronics. We're often measuring amplitude and phase or transfer functions, but it was repurposed to measure the amplitude and phase induced by tissue. And then in these devices, it's more down to custom analog electronics. And then my lab had worked on this for quite a while as well. We built this device, which is all based on digital electronics. So if you can see down here, we have laser driver, something called a bias T. So the laser driver provides DC currents. These DDSs, these are direct digital synthesizers. They generate the RF signal that we use to modulate the laser diode. The bias T just combines the AC current and the DC current to drive a bank of laser diodes. Light goes into the sample. We detect with an avalanche photodiode, which I haven't told you what that is in detail, but it's a photodiode that is biased at several hundred volts. So you're in this so-called avalanche state, so that when a photon is incident on the photodiode, it doesn't just produce one electron. One electron actually causes then two electrons to stimulate four electrons in this avalanche-like process that provides intrinsic gain, a gain of about 100, allows you to measure much lower intensity signals. And we need this because the light intensity for the frequency domain, it's very challenging, more than CW, since you're not integrating, you're measuring just at a single modulation frequency. You don't have that many photons to deal with. You need a very sensitive detector. We send the signal from the avalanche photodiode into a very fast analog to digital converter. We've played with different acquisition speeds. We kind of settled on 250 megasamples per second. Even when we take measurements that are past the Nyquist band for this analog to digital converter, we call this downsampling. And so you can calculate the amplitude and phase of, let's call it a 1 gigahertz sinusoid. Even if you sample at 250 megasamples per second, amplitude and phase is conserved in the downsampled signal that you collect with that analog digital converter. It's kind of a useful trick in electronics, and if you don't know what I'm talking about, it's not really all that important, but allows us to use cheaper electronics to take these very precise measurements. And then we have this hardware that we worked on for several years, combine it with firmware processing with an FPGA and an ARM processor. So we're calculating, not using Fourier transforms, but a version of a Fourier transform called the Goertzel algorithm that allows you to calculate amplitude and phase at a given frequency without calculating amplitude and phase at other frequencies you don't care about. It's just a more efficient algorithm that you can put into the FPGA. FPGA, a field programmable gate array, is it's a piece of hardware that you can program that's very, very fast. And then we use a deep neural network inverse model so that we could calculate optical properties at about 27 hertz. And so as far as we know, this is as fast as anyone's been able to take these measurements. If we don't do the real-time inverse model, we can actually take measurements in the kilohertz range, which when we first were able to do this, we thought was super cool. And it's been about 8 years and we can't figure out what it's useful for. So let me know if you have any ideas. Measuring fairly fast is useful, but measuring at kilohertz in the frequency domain, I don't know. And so here's an example of this video. Hopefully it'll play. Yeah. This is a source and a detector fiber on a thumb. And what you're looking at is a real-time extraction of oxy and deoxyhemoglobin, all measured from the frequency domain. So we do have mu A and mu S prime. And this pulsatile signal is from each beat of the heart, the cardiac signal. And what's kind of cool here is we published scattering. Scattering changed during the cardiac cycle. We didn't really think people had shown that before. And this, we talked about it for years, what's causing that. It could be as the red blood cells flow through the arteriole. Red blood cells, are flat, and they're probably at many random orientations and diastole. And then in systole, when the pressure builds and the blood velocity increases, what's thought to happen is all those red blood cells kind of align towards the wall of the arteriole. And that may change scattering or G, the anisotropy that we're measuring as a mu S prime from the surface. We don't really know. Yeah.
Also, the actual volume that you're probing
Yeah,
slightly
could be a
shift
partial
too,
volume, yeah.
because you have a displacement of blood through the volume that you're probing, and it could be a partial volume effect as well.
That's like the less exciting hypothesis, but let's just explain that. So in the reflectance geometry, this is can happen not just with frequency domain, but any of these techniques. If you have a change in blood volume, you have more oxygenated or deoxygenated hemoglobin, it absorbs very strongly. So maybe at systole, when you have more blood volume, your photon penetration depth actually changes. If you have more absorption, it's just harder to get photons deep. They get extinguished. So that means the measurement that you're taking, the measurement volume that you're measuring, is actually changing over time as well with each beat of the heart. And if you're in a layered structure, like the finger, where you have skin that has one scattering value and absorption value, and then maybe subcutaneous fat underneath, and then an arterial, you might be measuring different portions of those layers that all have different optical properties. So a perceived change in optical scattering at the surface measurement may not be because the blood is changing its optical properties, but because you're measuring maybe more superficially, and the larger portion of your measurement volume is from skin during systole. And then during diastole, you're measuring deeper. So your measurement volume includes skin and adipose tissue and so forth. Hopefully that was a reasonable explanation. We call that the partial volume issue. And so practically, here's like a handheld device. This was developed here at Beckman. This is kind of large because it incorporates an avalanche photodiode directly on the probe, and that goes directly on tissue. Not using a fiber to deliver light actually saves you a lot of photons. And we've used this to measure breast cancer patients. I'll show you that data a little bit in a few slides. We've also used it to measure many different parts of the body. This is oxygen saturation measured over 1/2 of a person, from their arms all the way down to their feet. And I really like this plot. It's interesting. I was unaware of how large the effect of being close to the core versus the periphery affects oxygen saturation. You can see in your belly, you're way up here at maybe above 80% oxygen saturation. As you get down to your foot, you're verging on 50%. And this is in a healthy person. It's really quite a dramatic thing. And this plot is just showing how total hemoglobin and lipids are correlated with each other. Just an example of types of things you can measure. Okay, yes.
So I've been accumulating a couple of questions already. So, you mentioned the relationship between time domain measurements and time frequency domain measurements. So, is there any relationship between continuous wave and time domain or time frequency domain? Also, you gave some details about the IRF for continuous wave measurements. So, what's the influence of the IRF in time domain, in time frequency domain? And I will stop
Yeah.
right now.
Two great questions, but the first one is already at least partially answered by Vasan. So in the time domain, if you integrate that measurement over the whole measurement time, you basically converge onto CW measurement. Right now, the relationship between CW or spatially resolved and time frequency domain, I mean, there's relationships in that we are segmenting out different path length photons or different arrival time photons. So there's an analogy there, but a direct transform, I don't know. I don't think we can do that. Like you could literally take time domain data collected off of a patient and do a Fourier transform and get it into the frequency domain and have data that would look just like you would with a frequency domain technique. To go from, yes. Yes, you can. You have to be careful there, right? Because the time domain incorporates so many frequencies. So if your sweep isn't long enough, you're going to lose part of that signal. Yes. I don't know how to go from spatially resolved to.
Not directly.
Yeah.
I mean, but I think the only thing that I would say is that when you are using temporal frequency domain methods, I mean, the light is continuously in the tissue. So but it's amplitude modulated in time.
Yeah.
But it is CW in the sense that you're constantly illuminating as opposed to putting in a pulse and looking at its temporal dispersion.
Yeah.
But I think the connection is all mediated through the time domain. Right? Because
Sure.
like you said, if you do a Fourier transform and yes, you have enough high frequencies, then you can reconstruct the temporal point spread function from a temporal frequency domain measurement.
Yep.
Yeah. But like you said, the time domain is the mother of all of those. So it mediates that connection. Yeah.
Did you have a second question? Oh, the IRF, yes. So the IRF of the time domain system will totally change the shape of that temporal point spread function, and you have to remove it. I'll show you a real world example of that in a few slides, yes. But
Either remove it. I mean, we've done some work in time domain, and what we do is that we generate the temporal point spread function of the instrument.
right,
And then when we generate a prediction from our model, we then apply the IRF to
There
the
you go.
model prediction. So you don't remove it, you add it to the model, and then you compare the distorted model prediction that's distorted based on the IRF with your measurement.
sure.
Right.
That makes total
I
sense.
think that's
yeah?
easier than actually trying to remove the effect of the IRF from the measurement itself.
Interesting, yeah.
And you definitely lose information.
Yeah.
Yeah.
Yeah. Okay. So let's finish up here with a comparison and some example applications. So I'll show you this table. We talked about continuous wave and spatially resolved measurements. Certainly the simplest, least complex of the methods. The disadvantage here is it can be difficult to disentangle mu A and mu S prime. You can do it under certain constraints, and we gave a few examples of them. Ideal use cases are things like FNIRS, where you're trying to look at delta mu A or delta oxygen-deoxyhemoglobin. Pretty good for deep tissue, though, with the caveat that it can be difficult to separate skull from brain. Often in FNIRS systems, you'll have close source detector separations and long source detector separations in order to do that type of thing, where the short ones are telling you about blood flow in the skull and long are telling you about the brain. Many commercial devices, like pulse oximetry, which I don't have time to talk to you about today or yesterday, is a CW technique. It's looking at a modulated signal, physiologically modulated signal, but it's using photodiodes and LEDs. Vioptics, Artemis, this is a near-infrared system, CW system that you can buy out of Europe. Hamamatsu makes some systems, and there's many more, right? Most commercial activity has been in this area. The spatial frequency domain, so non-contact, you get mu A and mu S prime at each pixel in the image. The potential disadvantages are shallow, medium complexity, right? You need a way to spatially modulate that light and a camera. Ideal use case, wide field but shallow, so skin or resected specimens. It's going to be hard to get down to muscle if you're measuring from the outside of the body in most cases. As far as we know, one company, Modulum, that's right here in Irvine, makes a commercial product. Time domain, mu-A, mu-S prime, deep tissue measurements, expensive, highly complex instrumentation. The players in this area, pioneers and kernel. I'll show you the kernel device in a little bit. And then the time frequency domain. Some similar attributes to time domain, somewhat expensive, less complex than time domain, typically cheaper than time domain, deep tissue, and you can buy an ISS device or near wave. Those are the two companies that I'm aware of. So let's look at an example of continuous wave. I wanted to show this to you yesterday. This is a SWIR probe we made. One in-gas photodiode. When you get into the shortwave infrared, silicon doesn't have quantum yield that's sufficient for measurements anymore, so you need a different detector. Semiconductor material, in-gas, has a lower energy band gap, so it allows you to detect those lower energy photons at longer wavelengths. We made this device that had 980, 1200, and 1300 nanometer LEDs, and these LEDs are spaced at different source detector separations, 7, 10, 13, and 16, largely dictated by how close we could get them to this photodiode, right? And then we space them out after that. But you can see this is a pretty classic spatially resolved measurement. Here, instead of having one source and multiple detectors, we have one detector and multiple sources. And what we wanted to measure is water and lipid in tissue with this device. And we used a neural network inverse model that was trained on Monte Carlo simulations, where input was diffuse reflectance at a given wavelength, at a given source detector separation. And so this was continued for all the source detector separations and wavelengths. But what we spit out was water or lipid. No stopover to compute mu-A and mu-S prime explicitly. The neural network may be handling that on its own, but the output is water and lipid. We trained this on 75,000, what I'll call synthetic tissues. So we did a distribution from literature of different potential optical properties we thought the tissue could have, different scattering values, absorption values, different chromophore concentrations, and made 75,000 synthetic tissues. Then use Monte Carlo to go from those synthetic tissue optical properties to expected diffuse reflectance at these wavelengths and source detector separations, and then built the neural network trained on that data to get that relationship between the measurements and the water and lipid. Here's the device, the actual hardware. Our first version was tethered to a control box. Our more recent version is Bluetooth enabled and battery operated off a little app. And we wanted to use this as a starting point to measure tissue hydration, which is something that wearable companies are really, really interested in, but there's also many medical applications. And we're also interested in body composition. So how much lipid do you have in your body? This is quite important for things like obesity, sports medicine, conditions and diseases called sarcopenia, or medical disorders like diabetes, type 2 diabetes, or cachexia. This is a wasting syndrome that can often happen with cancer patients, where they just start losing weight and people aren't really sure why, and it makes a bad situation worse. And the current methods we have to quantify body composition, it's typically defined as the fat, water, bone, and muscle composition of the body, is DEXA, this dual energy ray X-ray absorptimetry. This uses low energy X-rays, and it can segment the body into these different components. And this is the gold standard, but it's clearly not portable. It has ionizing radiation, though at low doses. And BIA, or bioelectrical impedance analysis, you may have seen these because some scales that you can buy at home have these built in if they have the electrodes. It works okay, but they have some limitations. Basically, the medical field hasn't adopted BIA because of concerns about low accuracy. So there's an interest in having alternative techniques that could measure water and lipid. So just to show you a little bit of data, we haven't been able to do DEXA scans yet, but you can do the skin fold caliper measurement, where you take this skin fold caliper and pinch the skin on subjects at a few different locations on the body. And then these companies have built up these charts where if you have your biological sex, your age, and then your skin thicknesses averaged over these different body locations will give you a body fat percentage. And that correlates really well with DEXA. The correlation coefficient is about 0.92. So we measured a bunch of healthy volunteers and looked how the skinfold-derived body fat correlated with this composite metric from our wearable. And we looked at water and lipid from the neural network and then just ratios of diffuse reflectance at different wavelengths. You can see in some circumstances we have really, really nice correlation. So this is just taking the probe and touching it in a few locations, the upper arm, the forearm, the wrist, and the calf. Unfortunately, the wrist actually performed the worst. It would be nice if your smartwatch told you what your body fat composition was over time, or at least it could be interesting for some segment of the population. But we found that you have to measure in different locations in order to get a good answer.
For the wearable, could you explain why the choice was made to have multiple sources instead of
Oh, sure.
multiple detectors? Because I feel like that would take more time, having multiple sources.
Doesn't take any more time, but part of it comes down to practicality. So this in-gas photodiode, first of all, it's a few $100, whereas the LEDs are just a few dollars. And the reason it's a few $100 is because the in-gas technology is at a much earlier stage than silicon technology. And this is a relatively large active area in-gas photodiode. The larger the active area, the more difficult it is to manufacture, and that bumps up the price. So unlike almost ubiquitous silicon detectors and CCDs, in-gas is just think like 30 or 40 years in the past. So this is the expensive, important component, and it's big. It's in a relatively large package. LED is dirt cheap. So just practical considerations like that. And for these measurements of body composition and hydration, we're not really expecting fast physiological dynamics. So a really fast measurement isn't all that important to us in this case.
Okay, yeah, thank you.
Yeah.
The diodes are smaller, so if you have multiple detectors.
Yeah, yes.
I also had a question about this slide. So did you run any like validation studies where you're with phantoms where you're adjusting like water content
Yes.
and lipid content if you're looking at water and lipid?
Absolutely.
Okay.
This is a topic that I like thinking about. So this is tricky. So how do you modulate lipid and water in a phantom? In tissue, lipid and water occupy a huge volume of the tissue. And the problem is if you change one, you typically also change the other, and then you also change scattering, right? Because the reason for that is lipids are highly scattering. The lipid emulsion and the micelles that contain the lipids, highly scattering to light, they're basically natural nanoparticles. So one of the things we do is we'll take an interlipid emulsion and just dilute it with water. But there we're changing water-lipid ratio and scattering. The other more fun titration we do is we'll make a liquid phantom with water, D2O, and lipid, typically soybean oil lipid. D2O, or heavy water, has between about 1/10 to 100th of the absorption of H2O at the wavelengths we're talking about here. So if you change the ratio of H2O to D2O, but leave the lipid composition the same, then you're not going to change scattering, and you're effectively, or I guess effectively is the right word, changing the water concentration, or at least the absorption of water, as if it's changing its concentration without perturbing anything else. But it's a good point. Like often when you're testing or validating a device, you want to change one variable at a time. And it's tricky in this kind of water lipid domain. That's trickier. That's trickier. And the other thing is intralipid, which we haven't talked about. This is a soybean oil emulsion that you can buy from medical suppliers or veterinary suppliers. It's medically used for conditions where people can't feed themselves solid or liquid foods. So you can get an intravenous injection of the soybean oil emulsion as nutrition. But it's been used by the biophotonics community for decades because it's fairly well controlled. There's lots of publications on the optical properties of intralipid. And so it can be quite useful. There are ways in which it doesn't match tissue optical properties. G, for example, goes very low, especially at long wavelengths. Those mismatch the tissue. But the other disadvantage is you can only go up to about 20% lipids. When we make phantoms that are higher than that, we have to make our own soybean oil emulsions. And there's a protocol for that. You basically buy soybean oil and you need a blender, an emulsifier, Triton X100, and you can make 50, 60% lipid concentrations, scattering while you're changing lipid concentration in water. Yeah.
Oh yeah, I actually had a really quick question about the power you used in your LEDs, but my system is like somewhat similar to this. So I might just pick your brain. If you had like inconsistencies in power or yeah, just more about the system. But actually, maybe I'll just ask you after because I might have just like detailed questions that
Okay.
no one else cares about.
Okay, sure. No problem. Happy to talk about it later. Yeah. Okay. So other CW or CW spatially resolved applications, I showed you these before. FNIRS is, this is a huge community. And they're not just people like us, like optical instrument developers. There's a lot of neuroscientists who use FNIRS technology, and there's commercial devices. So this has really been adopted in academia as almost a standardized tool. Then pulse oximetry is one of the great success stories of biophotonics. Been around, at least since the 80s and beforehand. And one of the most ubiquitous biomedical measurements, just that's the end of the sentence. Yeah. So major, major success story for us. And then skim flap monitoring, I showed you that. There's some commercial technologies there. Muscle size exercise studies. So if you look up, often it's called NIRS, the CW technique, there's thousands of publications each year. By far, most activity. SFDI. Okay. So we talked about the advantages and disadvantages. I'll take you through a few example applications. We used SFDI for years for measuring subcutaneous tumor models in the back of mice. And this is because we were also doing breast cancer studies simultaneously in humans with time frequency domain measurements, but we wanted to see how different therapies affected the tumor, and SFDI was the right technology. It was imaging technology. These tumors were just under the skin of these mice, so relatively superficial. So we would track anti-angiogenic therapies, chemotherapies, different types of small molecules, and we published on that a lot. So that's one example. You can see just here at day 0 and then day 12, this is a cytotoxic chemotherapy where the tumor volume's increasing, the hemoglobin levels are increasing. The scattering changed. We found scattering changed a lot in tumors that were treated. This is a collaboration we did again in mouse models where you're looking at a stroke that's induced in the surface of the brain of a mouse from a pulse from a laser. And over a period of a few hours, you can see scattering change at the core of that stroke. Brian Pogue's group up at Dartmouth, he was at Dartmouth and Wisconsin, he's coming back to Dartmouth. They use very high spatial frequency SFDI to look at breast margins. So in these resected specimens, they made maps of not just MUS prime, but the scattering slope and some different, more nuanced aspects of the scattering anisotropy. We've talked about G. G is one value that can quantify the average cosine of the angle of scattering. But if you measure at very high spatial frequencies where you're sensitive to very short path length photons, you can actually get information about the second order scattering. So if you take just this polar plot of scattering, there's actually more nuance to it. You can quantify those and use those as biomarkers. And they found that useful for identifying margins in breast cancers. We have a big project in our lab now is in scleroderma. I showed you this yesterday. You see a little bit better here. Here's a healthy control in a scleroderma subject. And then just the MUS prime map at 851 nanometers. And what's happening in the scleroderma subject is fibrosis is building up in the skin, in the dermis of the skin. But we think the fibril diameter of the collagen is actually smaller than in healthy tissue. So even though there's more collagen, the scattering is reducing because of the makeup of the size of the scattering particles in the skin. And then the company Modulum has been working to try to build SFDI as a platform technology for detecting foot ulcers or those who are at risk of developing foot ulcers. So what you're seeing here is total hemoglobin concentration in the foot of somebody that is healthy, somebody with type 2 diabetes, somebody with diabetes and neuropathy, then somebody with diabetes, neuropathy, and retinopathy. And as you go from left to right, there's more endothelial dysfunction and small vessel dysfunction. And you can see the total hemoglobin levels are dropping. And then if you see a hot spot, this appears to be a good indicator that an ulcer may develop in this patient at that location. And this is a big deal because ulcers are very hard to treat, to manage, and to cure or have that patient become healthy again because there's so much endothelial dysfunction. It's just hard to get that area perfused. But if you can identify in which people this is going to occur, you can intervene earlier and help the patient a lot and potentially save a lot of money. We made a hyperspectral version of SFDI that went out into the shortwave infrared. This is a fairly traditional SFDI setup, but here we're using a femtosecond pulsed laser. We're not using the pulse. We're using it as if it was CW. It's just the laser we use for multiphoton imaging in our lab. It's useful because it's tunable. So we're measuring over long integration times. The pulsing really has no effect, but we can tune it from 680 in the near infrared up to 1300 nanometers. And so we can tune the laser slowly and take lots of different measurements, and this allowed us to get at water and lipid. So for example, we did a study where we injected PBS, basically water under the skin of a mouse, and then measured with the system every 5 minutes and extracted the water concentration at these longer wavelengths past 1,000. And so here's an example of this mouse. This is the injection site, and the color tells you how much water concentration has changed right after that 5-minute injection. So when we don't inject anything, it doesn't change at all. After 0.1 milliliters of PBS, you can see that near the injection site, there's an increase in water. And as we increase that dose, you can see more. And then if we track these mice over time, we can see that water increases and then subsides as that PBS or water is absorbed by the mouse and goes away from that injection site. And so the more relevant clinical relationship here is in inflammation. So in this mouse, we just injected PBS. In this mouse, we injected this substance called TPA. You can see the chemical name here. This is a substance that's inflammatory. It causes increase in white blood cells, which we showed in the blood of the mice, and it causes fluid to accumulate around the injection site. And so take a look at these longitudinal plots. If you compare the PBS mouse, the water increases and then comes back down over time. But in the TPA mouse, where there's inflammation, water increases from the injection and then continues to increase as the mouse elicits more edema to the site of that inflammation. And it doesn't clear up until, after we stopped measuring. So this has relevance related to healing, inflammation, cancer, things like burn wounds, and knowing the severity of how bad the inflammation is, which could help you determine a treatment option. We also map lipid content in tumors. So this would be related to, for example, margin detection. Grew tumors in the back of mice, then resected them and did IHC. So you can see this is a white light image of a tumor that's been cut in half. And here's the lipid map where you can see areas of high lipid and low lipid. Then we looked at oil redo staining, which is an immunohistochemistry stain that's sensitive to lipids. And we did correlations between the lipid fraction determined optically versus with histology. And as, for example, breast tumors grow, they typically push out the natural fat in the breast. So knowing something about where the lipids are could tell you if there's tumor there versus fibrotic tissue versus adipose tissue. Other SFDI applications that have been explored in the literature, burns and wound healing or wound prediction, which we talked about for the ulcers, tumor margins, skin cancer, other skin pathologies. There's some work that's been done in endoscopy, trying to integrate SFDI into an endoscopic probe, but that's in earlier stages. And I'm giving you 2 review papers here on that are related to SFDI that you can dive into if you're interested in learning more. Yeah.
Darren, are you shifting to time and temporal frequency domain applications?
Sorry, say again?
Are you shifting to time domain and temporal frequency domain
Yes.
application? Might I suggest we close here and then we present those after my lecture, which is going to be shorter anyways?
Oh, interesting. Okay.
Because we have, it's getting to be 10. I want to I mean, there's a lot of stuff already to ask questions about
Yeah.
and then give them a breather and then.
And your lecture will bring a lot of this together in another
Yes.
way, and then we
And
can
then we
reinforce
can-
it with the other
yeah,
example applications.
Yeah,
Sure,
I think so.
totally fine.
That'd be great. Let's thank our speaker. Questions?
Oh, no, they should go first. They should go before me. Okay.
So can you go back to the slide where you showed the, I think it was oxygen saturation at different locations of the body, like the arm,
Oh, yeah, yeah.
breast? There, yeah. What was the position of the patient when doing the measurements? Was the patient standing, was sitting, lying on their back?
We took this measurement maybe 6 years ago.
Mhm.
My student did it, so I don't remember their position, but I do remember it took a long time
Yeah.
to take all these measurements.
Mhm.
So they were probably sitting or either laying down, but I'm sorry, I don't remember.
Yeah.
But
And I
yes,
guess
things would change as you change
yeah, that
position.
was basically the question. If you notice changes or if you expect changes with the position.
Yes, exactly. And
Mhm.
you expect some temporal dynamics as
Mhm.
well, right?
Yeah.
As things settle out.
Mhm.
Yeah.
Yeah. That's it.
Bernard?
So my question is on intralipid.
Yeah.
I know it's used as a scattering agent, but how do you model its absorption? Do you consider it as like part lipid, part water, or?
Yeah. And then you just use Beer's law, the lipid concentration to get at mu A.
Okay.
Give me a second. Intralipid. Address your question. I say mu A easily calculated from Beer's law. But like here's a intralipid comes in these pouches. So it's 20% volume by volume of lipid. So you can take that 20%, the extinction value from literature sources I mentioned. You can calculate mu A based on that. But you're assuming the vast majority of volume in intralipid is just water and lipid. There are some proteins in intralipid, but very small percentage.
So we can
Typically.
like, it's acceptable to ignore the proteins in the intralipid? Like it's still accurate?
It depends on how much accuracy you need for what application, but we tend to ignore the contribution from protein.
Okay, and do you know where you could find like intralipid? Have people measured the absorption? Have people made the spectra of
Yes.
intralipid?
Yes, many people. So this plot here is focused on mu S prime of intralipid. And what you're seeing is for 1% intralipid solution, published scattering, and then 10% intralipid published scattering from Flock et al. This is a very highly cited paper. And then another one from Aeronauts. You can see a problem here. Those don't match. So there's some discrepancy in the literature about intralipid optical properties. So does intralipid change over time by the manufacturer? It might. The particle size distribution might change. That could be part of it. The measurement techniques could change. It's also harder to measure higher concentration of lipids. You have this, especially for scattering, you have this thing called dependent scattering. Imagine if you have a whole high density of scattering centers, one scattering center can basically shield another from light. And so it operates in kind of a nonlinear way that can be difficult to predict with, say, me theory. But at low concentrations of intralipid, people have actually taken samples of intralipid and done electron microscopy to get the size distribution of the intralipid micelles. And once you know that, you can use me theory to predict the overall mu S prime.
Okay, very interesting. Thank you.
Yeah. I think, let me just show you this slide too. I mentioned this G. So these are literature values for anisotropy of intralipid as you go from 400 out to 2000. And you can see they don't all agree with each other, but directionally they do. They're all dropping dramatically as you go to longer wavelengths. And this is very different than what we think happens in tissue, where that G value probably stays pretty high. This is that figure from Steve Jacques' review paper. Now, there's much less data out here in the shortwave infrared, but there's not too many indications that G is really low, like it is in intralipid. So keep that in mind, right? If you're just trying to, if you're using intralipid to calibrate, for example, mu s prime equals 1 minus G times mu s, you kind of need to know what G is. You can't just assume it's 0.9. And so we have used intralipid as our calibration phantom, but we use the G value that we know, well, hope we know from literature. And then our forward model is a little bit different than our inverse model, right? Because the tissue is going to have a different G value. Yeah.
I just have a practical question about, so, absorption is, trying to get absorption and scattering, but sometimes some of the measurements are more complicated or they can take longer to collect the data or to analyze the data. So just, I guess if we go with continuous wave, just like reflectance imaging versus SFTI. Like, I don't know what your thoughts are. Like, let's just say you get a baseline measurement that you think is good of absorption and scattering. And if you're measuring something, you're doing some dynamic measurement or something, could you just measure reflectance at that point and then just assume this scattering? I mean, what are your thoughts on that?
Yeah, this is a standard trick.
Okay.
So I think what you're referring to, for example, for SFDI, you have to project a pattern, and you might want to, at a minimum, you project at 3 different offset phases, so 3 image captures, and then you might want to do that at multiple spatial frequencies, so you have to do that again. Now you're up to at least 6 images, and multiply that by the number of spatial frequencies you're interested in, and then different wavelengths. That can take a long time. So if you're trying to capture the dynamics from a cuff occlusion or some fast dynamics in the brain, you might not have time to collect all that measurement. But just like with FNIRS, if you can make assumptions about what's going to happen in the tissue. So for example, if you can assume that scattering is not going to change over the dynamics that you're measuring, then what people do is just switch to planar illumination. You know the baseline optical properties, BOA and mu s prime. You can use the planar illumination, the diffuse reflectance, to still calculate changes in oxy and deoxyhemoglobin or water and lipid, whatever you want, under the assumption that the scattering has stayed the same as your initial measurement. Yep, and this is a smart thing to do. You have to kind of convince yourself that the scattering isn't changing. No? Yeah.
Thanks.
We've also done that with the time frequency domain when we were first trying to capture cardiac dynamics. I would get the baseline optical properties and then just measure with DC, which is faster.
Other questions? I want to return to the intralipid issue again. I just want to, I don't know in these various papers what the methodology was for determination of optical properties, but I just wanted to remind the students about something we chatted on the first day about the limitations of radiative transport theory relative to Maxwell's equations. Because Darren, you were talking about, a 20% volume fraction of the soybean emulsions. And, if you're using, I don't know what models they use to recover optical properties, but if you're using radiative transport theory, that can be problematic with emulsions with such high volume fractions. Because remember, recall that in radiative transport theory, the intrinsic assumption is that every scatterer lies in the far field, the optical far field of the other scatterers. Because as we mentioned, once the scattered field is generated at a particle, it actually evolves. The angular distribution actually evolves on a spatial scale of about 6 to 10 particle diameters before it reaches a far field. So that means that the phase function is evolving in that near field. But as you said, if you have another scatterer in that near field, then it fundamentally changes the nature of the scattering. And so if we're using a radiative transport context to figure out reduced scattering, it may be problematic.
Yep. We did this recently in the past few years in blood. We were trying to measure the optical scattering of blood. And if you increase the hematocrit, concentration of red blood cells, you'll see over a certain period, as you increase the concentration, mu s prime increases linearly. But then once you get past a certain point, it starts plateauing off. right? You have this nonlinearity, and that's that shadowing, the dependent scattering effect. It effectively looks like there's fewer scattering particles because one is protecting the other, and for the technical reasons that Basan just mentioned.
I have a question about your last comment, and it's related to something that we discussed in the first day also, I think, which is you just mentioned we need to assume low dilutions, like to have the particles, the scattering particles far away, and you can translate that into time ranges. And I remember one of the slides that you mentioned it could be ranges between tenths of nanoseconds up to a few nanoseconds. But now when we measure in time domain, the distribution of time of flight of photons, that's already in the nanosecond scale. So does that mean that the first times of the plot are not accurate enough, perhaps, or what can we interpret from that?
So I think we're going to address these issues in this next lecture in maybe too much detail, but in the detail necessary to answer your question. Yeah.
Let me just say one more word about the D2O phantoms. This is just a slide related to that. We made these D2O phantoms where we're changing heavy water and regular water. And we have a frequency domain system that can measure into the shortwave infrared. Just look at this plot. This is mu A versus wavelength. As we change the ratio of D2O to H2O, you can see we can really change the absorption, and the absorption peak at 980 and then here at 1200, which is due to water, changes dramatically, but the scattering in these phantoms stays pretty constant.
So do you not account for oxygen saturation at all because it doesn't go that far into the sphere? Or it
Well,
has
in this
low?
phantom, no hemoglobin,
Yeah.
right? So we take out that complication, but of course in tissue you would.
Mm-hmm.
And we've done other simulations that show, at that 980 peak, oxygenation and hemoglobin concentration will have influence, but way out here at 1200, much less influence. Once you get past about 1150, hemoglobin concentration and oxygenation really affects your mu-A very little in most tissues.
Okay.
Another reason to go out to SWIR if you want water and lipid and you want to be insensitive to hemoglobin.
Do you just make these phantoms yourself?
Mhm.
Okay.
D2O is expensive though.
Oh,
It's
really?
hundreds of dollars or thousands of dollars for a relatively
Oh.
small volume.
Okay. Because I need to do this too for my experiment, and I'm trying to figure out if I should just purchase it
Yeah,
or if I should make it myself.
yeah. You can get it off of Sigma, but yeah, it's expensive.
Okay. Thank you.
Any more
Okay.
questions? Okay, let's close, and I'm sure we're going to continue this conversation.
Sounds good.